Welcome, dear structural engineers and civil engineers. So we have solved lot many problems related to simply supported beams. This time we will try to find out the deflection at the center of simply supported beam, which is subjected to uniformly distributed load W per meter. For this, we will find out the central deflection, and also we will try to find out the slopes at point A and point B, that is theta A and theta B. We will be using the conjugate beam method to solve the problem. Yeah, here we go. Now this slide gives you an idea about what we are going to do. As I told you already, this simply supported beam AB is subjected to uniformly distributed load W per meter, and the span of the beam which is simply supported is L. We will be finding the slope and deflection of this beam. At the center we will determine the delta C, and here we will find out the theta A as well as the theta B. Now, as I told you, this slide will give you the pictorial representation of what we are going to do. We will find theta A, theta B and delta C. Now, the first part is, first of all, we will be using equilibrium equation, that is summation of all moments at the point B is equal to 0. So this equilibrium equation 1 is used, and RA multiplied by L minus this W into L is the total load. So this represents the loading, and L by 2 is the lever arm distance, because the centroid of the whole loading is at the point which is at the center, and this center point is the centroid of the loading as well as it is at a distance L by 2 from the point P. Using this, we will calculate the value of RA, which is equal to WL by. Now, because of symmetric loading, you will be getting RB is equal to WL by 2. Also, you can verify this by using equilibrium equation 2. It says that summation of all forces and reactions which is acting vertical is equal to 0. Now the total load is W per meter multiplied by M. You can see that this is the total load, and already we have found out what is the value of RA, which is WL by 2. Substituting all the values, you will be getting RB is equal to WL by 2. This table will give you the results, that is RA equal to WL by 2, and RB, here it is RB equal to WL by 2. Okay. Now we will try to find out the expression for bending moment. So it's very simple. You take any distance x from the point A. At this distance, you are going to find out the moment at this cut. So you will find out what is mx. So mx is equal to RA times x. Here it is written RA times x minus, so this is W multiplied by x is the total load, and this total load acting in the span that is up to this distance will be acting at this point. So you can see that this is the centroid of this x. So the centroid of x length is nothing but x by 2. So here you will find out that W multiplied by x is the load, and this x by 2 is the lever arm distance. So this is the general expression for finding out the bending moment at any point x from the left hand A. Now it is equal to RA times x minus WX into x by 2. So RA already we know that it is L by WL by 2. Substituting these values, now here we will find out the bending moment at point A. So this is the bending moment expression, RA multiplied by x minus W into x into x by 2. Now at the point A, the value of x equal to 0. At point B, the value of x is equal to L. At any point center, the value of x is equal to L by 2. Yeah. First, we will find out what is the bending moment at this point A. Where x equal to 0, you will find out that the moment is 0. And here we go, proceeding further, we will try to find out the bending moment at the center. So this is the general expression is RA times x minus W into x by 2. So at this point, x value is equal to L by 2. You substitute this value in this expression. So if you do that, you will get RA into L by 2 minus W into L by 2 into this x is L by 2 divided by 2. So substituting RA equal to WL by 2, finally you end up with the value of WL square by 8. Now we have found out the value of bending moment at x equal to 0 and also x equal to L by 2. Now we will find out the bending moment at the point B. So this is the general expression RA times x minus W into x by 2. You substitute the value of RA as WL by 2 and x equal to L. Here also you substitute the value of x equal to L. So substituting all the values, finally you end up with the value as 0. So the bending moment diagram will be something like this, where here the bending moment is 0, here the bending moment is 0, at the center the bending moment is WL square by 8. So this is shown to you here by the tabular column. After calculations, we end up with m at x equal to 0 and m at x equal to L by 2 is WL square by 8. And at x equal to L, the value of bending moment is 0. Now the same beam is the beam which was solved earlier is called as the real beam, and the next to real beam we go and solve the conjugate beam. Now the point is, note on that this is the bending moment diagram for the real beam. Okay. Then what do we do? This bending moment diagram is taken to be the load for conjugate beam. So this conjugate beam, here the support conditions are similar to the real beam, that is simply supported here, and the loading has been divided by EI. So you can see that the maximum bending moment is at the center C dash, which is said to be WL square by 8 EI. We divided by EI. This diagram is called M by EI diagram. Technically speaking, this is moment divided by flexural rigidity. So now we will solve this conjugate beam. I will be finding only the reaction at point A dash, reaction at point B dash, and also at the center I will calculate the moment MC dash. So only I will be calculating this, nothing more than that. Now here, to find out the support reactions, what we have to do, we have to use the equilibrium equation, summation of V equal to 0. RE dash plus RB dash minus, this is the load diagram. So you can see that the total load or the parabolic load is 2 by 3 into base into height. So what is the base here? Base is L. So it will be 2 by 3 into L. And what is the H here? H is WL square divided by 8A. This is mentioned here, 2 by 3 times L into WL square by 80I, and this is the total load. Total load is nothing but the area of the load diagram. Now RE dash plus RB dash minus the total load is equal to 0. From this you get this expression, RE dash plus RB dash is equal to WL square by 12EI. Yeah, proceeding further, here you can see that we will use the equilibrium equation. Summation of moment at B dash is equal to 0. So RA dash is the load, it's a reaction, internal reaction RA dash for the conjugate beam multiplied by L minus 2 by 3 into L into WL square by 80A. So this is 2 by 3 into base into height. As I told you, this is B and this is H. So this is the parabolic load. And what is the lever arm distance? So for this total parabolic load, the centroid at this point, which is at a distance L by 2 from the point B dash, so that is being substituted here for the bending moment expression. There is moment at point B dash is equal to 0. So from this, after simplification, we get RE dash is equal to WL cube by 24 AI. Now use the equilibrium equation, summation of V equal to 0 here. So here it is summation of V equal to 0. So as you observe carefully, since this loading is symmetrical, directly you will be getting R dash B is equal to WL cube by 24EA. However, if you use summation of V equal to 0, substituting all the values, finally you end up RB dash equal to WL cube by 24EA. So proceeding further, here I have solved the reactions of the conjugate beam. I've got RA dash is equal to WL cube by 24EI and RB dash is equal to WL cube by 24EI. Now we are left out with only thing, which is said to be moment at the point C dash. If you know the reaction, you can easily calculate the moment at the center. Now we will calculate the moment at the center for the bending moment at the center for this conjugate beam. So as you see here, WL cube by 24EA and WL cube by 24EA are the reactions of the conjugate beam. Now proceeding further, here you go. Now we are concerned with the point C dash. So we will be considering only this loading, because we will multiply this RA dash by L by 2 minus half of the loading. So you can see that centroid of half of the parabolic load have to be considered to find out the moment at the center for the simply supported conjugate beam. Now you can see that this green color circle represents the centroid, which is at a distance 3 by 8 times L by 2 and from C dash, and the same centroid is at a distance 5 by 8 by L by 2 times from the point A dash. Now proceeding further, you will find out that here again the explanation is given that half of the parabolic load. So this is said to be half of parabolic load, which is obtained here, that has to be used. And for this half of the parabolic loading, we see that the centroid is at a distance 3 by 8 times L by 2. And this distance from point A to C dash is L by 2. As we know, it's obvious. So half of the parabolic load is considered. Now we are going to find out the moment at the C dash is equal to RA dash multiplied by L by 2. So this is the loading RA dash multiplied by L by 2 minus, then you have here half of the parabolic load as 2 by 3 times base into height. So this is base into height, 2 by 3 into L by 2 into WL square by 8 A. The point here is you will be getting half of 2 by 3 into L into WL square by EI as the half, means half of the parabolic load. Parabolic load that is 2 by 3 into L into WL square by 80. Now you can see how this is being calculated. So now this is the area of the half of the parabola, area of half of the parabola. Okay, and this 3 by 8 times L by 2 is the lever arm distance of half of the parabolic load. Now it's clear, the load multiplied by lever arm distance. Substituting all the values and final simplification, you end up with m dash c is equal to 5 WL power 4 by 384 L. Now I have calculated the moment at the center for the conjugate beam. Now these are the tabulations. Now you compare the conjugate beam with the real beam. So the RA dash is the shear force at the point A dash for the conjugate beam, and RB dash is the shear force at B dash for the conjugate beam. M dash is the bending moment at C dash for the conjugate beam, and these are the equivalent to theta A, theta B, and del C for the real beam. Now we have derived the slopes at point A and point B of the simply supported beam, and also we have derived the deflection at the center by using conjugate beam method. So these are the values which we are interested in. You can use any methodology, but here I have chosen the you can use strain energy method also, and here I have used the conjugate beam method. So thanks a lot for watching. If you have any doubts or queries, please mention in the comment section.